All right, so we'll talk about resonance in a series RLC circuit. Okay, so what we're doing is, so here's a series RLC circuit. And what we are going to talk about is when is maximum power delivered to this circuit. Okay, and from this expression, you know that maximum power is delivered when phi is 0. Okay, let's see when will phi, phi is, maximum power is delivered when phi is 0. When will phi be 0? Let's look at this expression. When will phi be 0? It'll be 0 when XL minus XC is 0. Okay. And so at that particular frequency, phi will be 0 and maximum power will be delivered to this circuit. Okay. And that's called resonance. So at a particular frequency, when phi is 0, XL equal to XC, and maximum power is being delivered to this circuit. All right, so that's called resonance, and an RLC circuit is in resonance when current is maximum. So current is maximum, current is voltage amplitude divided by, or IRMS is VRMS divided by the impedance. When the denominator is minimum, then current is maximum, and denominator is, see, this is not dependent on frequency, only this is dependent on frequency. And so when that guy is 0, implying when the frequency is 1 over square root of LC. So let me show you that. Okay, so XL, what you want is XL minus XC to be 0. XL is omega L, and oops. Okay, so at this frequency, and that's called the resonant frequency. At that frequency, you'll deliver maximum power to the RLC circuit. Okay, and phi is 0 at that point. So, so what you want is the reactive, inductive reactance to cancel the capacitive reactance, and that's when you'll deliver maximum power. And so that's what I showed you a minute ago. So here's the power plant. The transmission lines have inductive reactances. Okay, they don't have any capacitive reactance, so they have inductive reactance. And so at the end, right outside the city, you put a bunch of capacitive reactances. So XL is canceled by XC, and then maximum power is delivered to the. So here's the bank of capacitors. So power capacitors are used to balance the impedance of the effective inductance in transmission lines, and thereby maximum power can be delivered to the city. All right, so the quality factor, like the current average power transferred from an AC generator to an RLC peaks at resonant frequency. So power delivered peaks at resonant frequency. So if you're at any other frequencies, XL and XC do not cancel. Only at this frequency do XL and XC cancel. Okay, and now this concept can be generalized. We are talking about, we were talking only in RLC series circuit, but so the sharpness of this resonance is given by a quality factor. It's a dimensionless quantity. So Q, the quality factor, tells you how sharp this peak is. So for instance, if your circuit was a tuning circuit, if you don't want disturbance from nearby frequency, what you want is a sharp curve. Okay, so the quality factor is defined as omega divided by delta omega. delta omega is the width at half power. Okay. And you see the smaller the width, greater Q is. And so the quality factor is related to the impedance, the inductance in the circuit divided by the resistance in the circuit. Okay, so let me show you a curve. And all right, so resistance. Okay, so here the average. So what we'll show you is we'll change the frequency of the AC source, and the power delivered, the current and the power delivered to the circuit will change with frequency. Okay, and you'll see. So for these frequencies, see the current is increasing. There's the, for that frequency, the current was maximum. That was the resonant frequency. And you see the power delivered is that peak. Okay, and there's the 2.5. That's the width at half maximum. Okay, and you can do the quality factor. Okay, so for a tuning circuit, you want this peak to be as sharp as possible. Okay, so that's the quality factor. All right, so if the quality factor of this circuit is large, meaning you want a large inductor and a small resistance. So remember, for the quality factor to be large, you want a large inductor and a small resistance. So if you have a large inductor and a small resistance in this tuning circuit, then the peak will be sharp and you won't get disturbance from nearby frequencies. Okay. So radio is tuned by varying a capacitor to match the resonant frequency of the circuit with the incoming electromagnetic radiation. All right, so going on to another topic, we talked about transformers last chapter briefly. So you have step-up transformers and step-down transformers. So voltage step-up and step-down transformers are used for power transmission. So for instance, at the station, power is generated, the amplitude of the power is about 12,000 volts, and you see transmission power is being transmitted at 400,000 volts. And so you have to have a step-up transformer. And then, of course, you don't want 400,000 volts coming into your house. So then you have to have a step-down transformer. Here's 13 kilovolts. And then this steps down to 240 volts, which is what's fed to your home. Okay. All right. So you have to have step-up and step-down transformer. And here's the input voltage and here's the output voltage. The output voltage is related to the input voltage like so, N2 by N1. So if N2 is greater than N1, then it's just V2 will be greater than V1, and that's a step-up transformer. If N2 is less than N1, then V2 will be less than V1, and then that would be a step-down transformer. Okay. So if you want to step up the voltage by a factor of 10, the number of turns have to be greater by a factor of 10. Okay. All right, so now we'll briefly talk about rectifiers and stuff. So many electronic devices require direct current. So your laptop works on direct current and so on. Your phone works on a direct current. But what you get out of the wall is AC current. So how the most easily available sources is AC source. So the process of converting an AC current to a DC current is called rectification. Okay, so can you guys see this? Where is my camera? Okay. Okay, so you guys see that?
Yep.
Yep. Yeah, so that's a, what that is doing is it's doing rectification. Okay. So, among other things. All right. Okay, so that's what this does. All right, so here's an AC source, and what you have is a diode, and here's your circuit. Okay, so what a diode will do is, this is the AC source, and a diode will only let currents pass in one direction. So when the current is flowing in this direction, it'll let the current pass. When the current flows in this direction, it won't pass. Okay, so the diode lets current pass only when the voltage on this end is positive. Okay, so for this cycle, it'll let the current pass there. So all the positive cycles, it lets the current pass. Okay, so but you have lost half the energy. Okay, so with just a single diode, all you get is these positive peaks. And this is called a half-wave rectifier. Now, if you want both the cycles in, you have to have 4 diodes. And if you connect this AC source with 4 diodes like that to your load, what you get is a full rectification. Okay. So this can be also shown like so. Okay. So when you have 4 diodes connected to your circuit like that, you get full rectification. But your cell phone and your laptop won't like this. What they want is a flat curve. Okay, and so we'll show you how to get a flat curve. So all you do is now connect a capacitor to this, and there's your load. So your load is connected across the capacitor, and the capacitor smooths out the voltage. So there's the full rectification. Okay. And so that's how rectification is done. Okay. So that's how an AC signal got converted to a DC signal. Okay. So you connected an AC source, and there was your load, and what you're seeing is a DC source. All right, so we'll talk about low pass filters. So if you have a DSL connection, if you had a DSL connection and a landline, now landlines are a thing of history. You don't see many landlines, but if you had a DSL connection and a landline, you would have a low filter like this. Okay, internet traffic is passed at the high frequencies, and voice data is passed at low frequency. Okay, so you had a low pass filter. So on the wires, you get many frequencies coming in, and you feed those frequencies, and at high frequencies, the resistance of this goes down, so you don't get any output voltage. Okay, so the circuit like this, if you're looking at the voltage out here, you can only see the low frequencies. Okay, so this circuit, if you will let only the low frequencies get through, and you see high frequencies, the current is minimal. Okay, so that's a low pass filter. So this circuit is a low pass filter. So this circuit connected to the source, and there's the output, and what you get is only the low frequencies coming through. So at very low frequencies, the output voltage is equal to the input voltage. And you see at about 7 megahertz, well, roughly 7 megahertz, the output voltage has fallen to half the input voltage. So at high frequencies, the signal is weaker. So this is a low pass filter. So in many applications, a superposition of many frequencies are involved. DSL internet connection operates at high frequencies. So the internet connection operates at high frequencies. So these high frequencies would cause noise on phones, the landlines. So a DSL connection uses your landline phone lines. Okay. So shown is a low pass filter connected to phones in home with a DSL connection. Yeah. So the signal to the phone goes through this, and only the low frequencies are let through this thing, which is what you want to feed to your phone. Okay. Here's a high pass filter. So if you flip the capacitor and a resistor, then that becomes a high pass filter. Okay. So these high frequencies are the ones that are used by your internet connection on a DSL. All right, guys, that covers this chapter. So what I'm going to do is briefly summarize the chapter again, and then open the floor for questions. So what we were interested in was the following. Okay, so we were going to connect an AC source to a circuit. This AC source was VT, the voltage as a function of time was V0 times sine omega t, and the current was IT was V0 times Z. Z is the impedance of the circuit, and there's a phase shift. The current lags by phi to the voltage. Okay, so the two things we were interested in circuits for this circuit were Z, the impedance, and the phase shift. Okay, so those were the two things we were interested in these AC circuits, and we saw that. So the current amplitude is E max over Z, and the phase shift is what we are interested in. Okay, so for a general circuit like this, we connected a pure resistance. Z is equal to R for the pure resistance, and phi is 0. We define RMS values, IRMS values. We define these values so that our expressions for power would look very similar to the DC power expressions. Okay. And RMS values are, IRMS is Imax over root 2. Similarly, VRMS is Vmax over root 2. Okay. When you connect a pure inductor to an AC source, this is Z. So Z is omega L, and phi is pi by 2. Okay, so the current lags the voltage by 90 degrees, or the voltage is ahead of the current by 90 degrees. Okay, so the inductive reactance is omega L. For a capacitor, the inductive reactance is 1 over omega C. Okay, and phi is minus pi by 2. So the capacitive reactance is 1 over omega C. And again, these resistances are frequency dependent. Okay. For an RLC circuit, Imax is Vmax over Z, and Z, the reactance is given by that. Z is R squared plus XL minus XC squared. XL and XC are dependent on frequency, and so Z is dependent on frequency. Okay. And the phase angle, the second thing we were interested in, the phase angle is tan inverse of XL minus XC divided by R. Okay. So this table summarizes Z and phi for these combinations. Okay, so they're all series combinations. We haven't given you anything for parallel combinations or a combination of the two. So for the very simplest case, here are Z and the phase angles. Okay. The power delivered to the circuit is IRMS VRMS times cosine phi. So phi is extremely important. So that's cosine phi is called the power factor, and that tells you how much power is being delivered to the circuit or to the city or whatever. Okay, so if you want maximum power delivered, you want phi to be 0 and cosine phi to be 1. Okay, so and for phi to be 0, XL has to equal XC for phi to be 0. Okay. All right, so and we saw that for a series RLC circuit, resonance happened when XL was equal to XC, so Z was minimum and current was maximum when XL minus XC is 0, and that happens at this frequency. So at this frequency, at that frequency, maximum power is delivered to this circuit. Okay. All right, so that's resonant frequency. And we saw that we adopt this kind of stuff in when power is being delivered to a city. Transmission lines have XL, non-vanishing XL, so you have to have XC before power is delivered to the city, such that XL cancels XC, and maximum power is delivered to the city. Okay. Here's the quality factor. Shows you the sharpness of the power peak with respect to frequency. Okay. And the greater the quality factor of this tuning circuit, the less the disturbance from nearby frequencies. Okay. That's a transformer. If N2 is greater than N1, then that's a step-up transformer. And if N2 is less than N1, then it's a step-down transformer. Okay. So here's rectifiers convert AC signals to DC signals. This is a half rectifier, and here's a full rectifier. It converted this signal to a DC signal, but this still is not good enough. What you need is a smooth output. And so here's a full rectifier. 4 diodes in this capacitor constitute the full rectifier, and you converted an AC signal to a DC signal. Okay. Low pass filters let through only low frequencies, and they block high frequencies. This is a low pass filter. So this is a low pass filter. And here's a high pass filter. A high pass filter blocks low frequencies and lets through high frequencies. Okay. All right, that covers the chapter.